Hey Chemistry, Mrs. KJ here for the last lesson of the year. Yay! 8.08 Review, Nuclear Chemistry. Review concepts presented in the lessons, transmutation of elements, and nuclear fission and fusion. Nuclear reactions can change one element into another with the release of huge amounts of energy. The change, or transmutation, can occur naturally as a result of radioactive decay or the fusion of elements inside a star. It can also occur artificially in particle accelerators or nuclear reactors. Either way, the energy released is orders of magnitude greater than the energy released in chemical reactions. So in other words, millions of times more. And this abundant energy can be harnessed to make electricity. Goals for this lesson: demonstrate mastery of important knowledge in the previous two lessons. Slide 2, of course, has the student guide. Key concepts in transmutation of elements. Transmutation of elements occurs through decay of natural radioactive elements and through the collision of atoms at high speeds. Unstable nuclei decay to stable ones by giving off radiation, which is particles, energy, and/or heat. You can have alpha emission, which means that it releases a helium nucleus. Beta emission means it releases a high-speed electron. Gamma emission means that it releases gamma rays, which are electromagnetic waves. You can also have positrons. You see it's just the 1, 0 electron. If you have the negative 0 electron capture, that stands for the electron. The nucleus captures an electron from the cloud. The electron combines with the proton to make a neutron. The neutron may be emitted. Remember, this high-speed electron did not come from the orbitals. It came from breaking apart in the nucleus. Radioactive emissions can change the composition of the nucleus and produce new elements and isotopes, which is the definition of transmutation. Particle accelerators smash high-speed particles into target atoms to make new elements or radioisotopes, and radiation. Key concepts in nuclear fission and fusion. Albert Einstein showed that mass and energy are equivalent, E equals mc squared, where c stands for what? The speed of light, which is 3 times 10 to the 8th meters per second. Chemical reactions have insignificant changes in mass, while nuclear reactions have significant ones and yield much more energy. In fission, heavy atoms absorb neutrons, split into lighter ones, and yield particles and energy. A critical mass is essential for a chain reaction. In fusion, lighter elements combine into heavier ones and yield particles and energy. High temperatures and pressure are needed. Nuclear power plants harness the heat energy from fission and will do so from fusion too at some point in the future. But right now, we only get nuclear power from fission as far as electricity. And what happens is it's used to drive steam turbine electrical generators. RTGs, are radioisotope thermal generators, use radioactive decay to make small amounts of electrical power for spacecraft. Nuclear energy comes from combining atoms, which is fusion, or splitting an atom, which is fission. And then we'll look at our problem book. There's a quiz, and then there are some other websites if you're interested in looking at those. So those are on slide number 7. Alright, so we will go to our problem set now. Transmutation of elements. Objectives: define transmutation, identify isotopes that are products of transmutation reactions. You can use a transmutation equation to predict the products of a transmutation reaction. Nuclear transmutation is a transformation of an atom of one element into the atom of another element. This can occur naturally or artificially. Both natural and artificial transmutations involve changing the number of protons in the atomic nucleus. Natural transmutation occurs when radioactive elements spontaneously decay and transform into other elements. Transmutation of elements can also be achieved artificially by bombarding elements with high-speed particles. Remember, transmutation. Transmutation occurs when an atom of one element changes into an atom of another element. Remember, that's very different from chemical reactions. Chemical reactions form different compounds, but they're always the same elements, what you start with, what you end with. Here and now, we're changing from one element into another element. Alpha emission and beta emission can accompany transmutation. Scientists can cause the transmutation of some elements by firing high-energy particles, such as alpha particles or neutrons, at other elements. Many of the transuranium elements are produced this way. So trans beyond so elements that have a higher atomic number than uranium. Complete a transmutation equation. Complete each of the following transmutation equations. Assume that each equation has only one known product. Alright, so we have 212PO yields 4He, and we have 84 and 2 for atomic numbers. Remember, across the top, they have to equal each other. So 212 has to equal 4 plus x. So solve for x up on the top. 84 has to equal 2 plus x. So solve for x on the bottom. And then you have to do the same thing for this one. So please hit pause and get both your answers. And so it says transmutation equations describe nuclear reactions. The superscript and subscript on the chemical symbol of an isotope give its atomic number and atomic mass number respectively. In a balanced transmutation equation, the sum of the atomic numbers, so all the subscripts, of the reactants must equal the sum of the atomic numbers of the products. And the sum of the atomic mass numbers, the superscripts, of the reactants must be equal to the sum of the atomic numbers of the products. The atomic number of the atom identifies its identity. And so then you just look on the periodic table to decide what it is. So use your algebra skills. Equation 1, going across the bottom, 84 equals 2 plus x. And across the top, 212 equals 4 plus x. For the second equation, 37 minus 1 equals minus 1 plus x. And 87 equals 0 plus x. And do the algebra, and you should end up with 208, 82, and lead. So you look for number 82 on the periodic table, and you find out that it's lead. The second one, you look for number 38 on the periodic table, Sr, and you find that the mass number is 87. If you have questions on any of this, please see me, and I will go over some more with you. Tip, a beta particle or electron technically has no atomic number or atomic mass number because it contains no protons or neutrons. However, for the purposes of writing and balancing nuclear equations, the electron is assumed to have an atomic number of -1 because the charge is -1, and an atomic mass number of 0. These numbers are used in calculations, but they do not actually describe the properties of the electron. Alright, so you got 3 problems to do. Complete the transmutation equation shown below. Assume that there's only one known product. And define transmutation in your own words. And then there's another one on the bottom. So please hit pause and do those on your own. When you're ready, hit play again. And question number 1. In a balanced transmutation equation, the sum of the atomic numbers of the reactants must be equal to the sum of the atomic numbers of the products. And the sum of the atomic mass numbers of the reactants must be equal to the sum of the atomic mass numbers of the products. So use your algebra. 92 equals 2 plus x. Solve for x. You get an atomic number of 90. What do you do with that number? You look on the periodic table and you find the element that has the atomic number of 90. Find your mass number. 235 equals 4x. X is 231. Your final answer should be written like this. The 90 should go on the bottom. That tells you that the element is thorium. And the mass number is 231. So it does need to be written in that format. Next question was transmutation. The change of an atom of one element into an atom of another element. And we have another one here. Hopefully you had a chance to figure that out. And our atomic number this time is -1 and 0 mass. So what does that tell you was spit out of there? Well, it tells you that it had to be an electron, okay, with 0, -1 right there. All right, as always, if you have questions, let me know. All right, let's go ahead and start the next set. Nuclear fission and fusion. Nuclear reactions release much more energy than chemical reactions do. Nuclear reactions are very different from chemical reactions. In chemical reactions, elements combine to form new compounds, but the elements in those compounds retain their original identities. In nuclear reactions, because now we're messing around with the nucleus and the number of protons, atomic nuclei interact to produce new elements. The nuclear reactions that are most common are fission, in which heavy nuclei break apart into lighter ones, and fusion, in which light nuclei combine to form heavier nuclei. Both fission and fusion can release many times the amount of energy released by even the most exothermic of chemical reactions. The enormous amounts of energy released during nuclear reactions are a result of matter being converted into energy. Energy and matter are related by the equation E equals mc squared, where E is energy in joules, m is mass in kilograms, and c is the speed of light in meters per second. Because the speed of light is a very large number, approximately 3 times 10 to the 8th meters per second, even the tiny amount of mass that is lost in a typical nuclear reaction produces a huge amount of energy. Objectives: contrast the energy released during chemical reactions with the energy released during nuclear reactions. Use the equation E equals mc squared to relate mass and energy. Remember nuclear reactions? Nuclear reactions result in the formation of new elements. In contrast, chemical reactions do not produce new elements. Mass is lost during nuclear reactions. The lost mass is converted to energy. The equation E equals mc squared describes the relationship between mass and energy. Identify nuclear fission and fusion. An atom of californium-248 can undergo radioactive decay to form an atom of curium-244 and an alpha particle. Is this an example of nuclear fission or nuclear fusion? In nuclear fusion reaction, light nuclei combine to form heavy nucleus. In a nuclear fission reaction, a heavy nucleus breaks down, or fizzes, that's how I think of it, fizzes apart into a lighter one. When californium decays, it forms two lighter nuclei. It forms the curium and the alpha particle. Remember that an alpha particle is a helium nucleus. The reaction involves a heavy nucleus breaking down to form two lighter nuclei, therefore it is a fission reaction. Oops, I must not have scrolled down enough on the last page. Sorry about that. Example 2. Calculate the energy released during a nuclear reaction. 1 mole of thorium-231 can decay to form 1 mole of radium-277 and 1 mole of alpha particles. The atomic mass of 1 mole of thorium-231 is 231.0363 grams. The atomic mass of 1 mole of radium-227 is 227.0292 grams. The mass of 1 mole of alpha particles is 4.0015 grams. How much energy is released during the decay of 1 mole of thorium-231 into radium-227? Alright, so hit pause if you can do it on your own. Go for it. Collect and strategize. The mass lost during a nuclear reaction is converted into energy released during the reaction. Therefore, to calculate the energy released during the reaction, first calculate the amount of mass lost during the reaction. Then use the equation E equals mc squared to convert mass to energy. To use E equals mc squared, mass must be in kilograms. The following information is given in the problem, so it lists it again. Now, if you're ready now, hit pause and do it on your own. If not, keep following along. Calculate the lost mass. During the reaction, each thorium-231 atom changes into 1 radium-227 atom and 1 alpha particle. The mass lost during the reaction is equal to the initial mass of 1 mole of thorium-231 minus the sum of the masses of 1 mole of radium-227 and 1 mole of alpha particles. The mass loss is calculated as shown below. Okay, so because theoretically the reactants should equal the products, but it doesn't because, again, some of the mass is converted into energy. So we have our reactants minus the sum of our products. And we have it as 5.600 times 10 to the negative 3rd grams. We need to change it into kilograms. You can either move the decimal 3 more places to the left or divide by 1,000. Use the equation E equals mc squared to calculate energy as shown below. So we have E equals our mass times the speed of light equals 5.00 times 10 to the 11th joules. As you can see, this is several orders of magnitude more energy than is released during a typical chemical reaction. Most exothermic chemical reactions do not release more than a few kilojoules per mole of reactant. This reaction released more than 100 million kilojoules of energy per mole of thorium-231. Tip